So I'll give a little introduction here to today's speaker, which is Svetlana Shkolyar from NASA Goddard Space Flight Center. Dr. Shkolyar actually overlapped with me for a couple years as collaborators on the Curiosity SAM instrument science team. And before that, so she has a sort of wide-ranging educational background, at least from what on her website. So a bachelor's in physics from the University of North Florida, a master's in mass communication with a sort of a science focus, I guess, from University of Florida. And then she was a NASA Academy intern at the Goddard Space Flight Center, which is another thing that we have in common, actually. Oh, so, yeah, Academy 2006 here.
Go Academy.
And so then she went to the University of North Dakota for their Space Studies Master's program, which is kind of a unique scope of program that's well known for that. So that's pretty cool. And then to Arizona State University School of Earth and Space Exploration for her PhD in geological sciences, which I think was with Jack Farmer advising. Is that right?
Yep.
Yeah. So with that advisor, became of course an expert on biosignature identification. Then went on to do a postdoc at the Carnegie Institution in Washington. Which is when she was involved with the SAM team, and now is at the Goddard Space Flight Center, I think as a NASA postdoctoral program fellow. Is that correct? Yep.
Only for like 2 more months, but yes.
Okay. Okay, great. And is now also a collaborator on the Perseverance Super instrument. So as I warned her at the start, we should all be ready with questions about Perseverance findings, which I don't know if that's what we'll hear about in the talk directly or not, but the talk is relevant certainly to the rover's investigation. So she's going to tell us about informing Perseverance Rover Biosignature Studies with Raman and Fluorescence Spectroscopy. So if you want to go ahead and share your slides, we can get into it.
Yes. Okay. Does that look all right?
Looks good to me.
Cool. So thank you all for inviting me here today. My work today in this presentation is going to focus on basically studies to inform the detection of potential biosignatures preserved in the rocks using the spectroscopy instrumentation on board Perseverance rover. So as some of you may know, the Perseverance mission has a main goal of being, an astrobiology mission, right? It is looking to seek evidence of past life in the form of biosignatures preserved in the rock. However, that is not the only objective of the mission. It is also going to continue our further understanding of the formation and alteration processes on Mars. It is going to cache samples for the first time to be brought back to Earth, which is quite an exciting era in Mars exploration. Of course, we have many samples of Mars on Earth in the form of meteorites, right? But those were sort of given to us by nature, and we had no say in where those samples came from or what kind of samples they were. And so this is going to be the first time where we're actually going to be caching samples for potential return, probably in the 2030s, hopefully, back to Earth. And those samples will be better investigated for their potential biosignatures using the more robust, fancier, higher resolution instrumentation we have on Earth. And so not only life detection studies, but for example, geochronology studies will be performed on those. And some of my non-astrobiology work is actually focusing on looking at the samples to be best dated on Earth for geochronology measurements. So, but of course, this talk will be focusing on the astrobiology aspect. Oh, and then human spaceflight, demonstrating and getting ready for ISRU, for example, is another big objective of the mission. So in terms of the rover payload suite, we have a variety of instruments that are quite exciting, including several firsts on the rover. Of course, we have a suite of, we have the weather station through MEDA, we have the oxygen ISRU instrument MOXIE, we have the radar, we have the Mastcam Z. And some of these instruments are sort of a new evolution of some of the previous instruments you may have heard that you may have seen used on previous rovers. We have a pixel instrument, the X-ray spectrometer, and the two spectroscopy instruments that I will be focusing on today, SuperCam and Shkolyar. These are both very exciting firsts for a Mars rover, really for any type of surface planetary exploration. This is our first set of Raman spectroscopy instruments flown to any solar system body, and not one but two on this rover are currently actively performing Raman spectroscopy analyses, as well as fluorescence spectroscopy. Many of you may be familiar with lab Raman spectroscopy, but I like to call fluorescence spectroscopy sort of the lesser known cousin of Raman. And I will show you why in this talk. I think that the combination of the two in one instrument, in one spectrometer, basically, can enhance your ability to identify biosignatures. SuperCam and Shkolyar are, of course, very different in their type of spectroscopy. SuperCam is a standoff, meaning a very distant instrument on the head of Percy, while Shkolyar is on the arm, and it is a contact sort of more close-up instrument. And it is a UV Raman and Fluorescence spectroscopy instrument. And both of them, of course, also include imagers, and SuperCam is a host of additional other capabilities, such as LIBS, laser-induced breakdown spectroscopy. Shkolyar is actually one of my favorite NASA acronyms. It is the best acronym. It is Scanning Habitable Environments with Raman and Luminescence of Organics and Chemicals. Great acronym, right? And of course, when they designed the camera, they had to name Shkolyar's camera Watson. So Raman spectroscopy has been really, sought after for planetary missions for a while, and we finally have one on Percy, two on Percy that have landed recently, but this was a long time coming. Raman has been in development for payloads for targets across the solar system for a long time, decades at this point. And for example, on the Europa lander mission, there was not only a baseline but a threshold payload instrument using two different types of Raman instruments, one modeled right after Shkolyar and one modeled after the RLS instrument is actually modeled after the European Space Agency's rover. So when ESA's rover launches, we will actually have a third Raman instrument on the surface of Mars. So why is Raman spectroscopy so valuable for biosignature detection? I'm not going to go through this in too much detail, but I'm just going to summarize a few key things that we love to do using Raman. First of all, you get a very unique spectral fingerprint of a compound with very narrow, precise spectral bands. Unlike many other types of spectroscopy, this is a much more precise fingerprinting technique where you can identify not only biosignatures in the form of organics, like, for example, macromolecular carbon preserved in a rock. That's my favorite biosignature and the one I'll be talking about today. But also the mineral matrix that is hosting that organic. We want to know in astrobiology, of course, where that organic came from, what its paragenesis is, how it, got preserved in that rock, what happened in the fluids surrounding it, and how all that sort of works together in a system to preserve that biosignature. So the minerals surrounding it are very important to us as well. And also, it's non-destructive. The laser bounces off the surface of the sample, and generally that doesn't. You don't have to powder the sample, for example, such as you would have to do with, for example, the SAM instrument on MSL. That is another very powerful organic detection instrument that we all have seen make some very exciting discoveries recently. However, the samples do have to be powdered and submerged in solutions, so it's a wet chem experiment. And unlike that, Raman does not destroy your sample so you can analyze it again on Earth. That's what we want. We want that sample to be brought back on Earth in the most pristine, little cache container possible. And then on Earth, we want to be able to relocate those potential biosignatures and continue the analyses and do the biogenicity analyses. A laser is quite fast and unlimited. There's not really a limit except, the rover operational and power aspects are really the limiting factor to how much you can, zap that laser. And there's no, as I mentioned, no sample prep. The trade-offs, however, no instrument is perfect. And the trade-offs with Raman are that you are able to fry the organics, like you can, cook them if your laser settings are too high. And you cannot actually prove that this organic component is indeed a signature of life. You can say that you have a potential biosignature, as I mentioned, in the form of, like, for example, macromolecular carbon. That can be, of course, the result of biomolecules being degraded and undergoing, sedimentation and diagenesis in the terrestrial rock record. So those can be biogenic, but they can also come from the same types of macromolecular compounds can also be delivered in a meteorite to Earth and be completely abiogenic. And we've seen this in meteorites, significant amounts of macromolecular carbon that has the same Raman spectrum as for example, kerogen, the biogenic form. But again, this is to identify potential biosignatures, and for that, Raman spectroscopy is excellent. The biggest problem you'll probably come across when reading about Raman spectroscopy is this fluorescence interference. So I'm showing what that looks like. It's in this spectrum, it's the blue spectrum where you have this basically very sloping, very broadband background that often overwhelms your Raman information. And that is a huge issue that we're actually mitigating in several ways on the Perseverance Raman instruments. But first, let me explain by sort of giving you a super quick physics 101 intro on the difference between Raman and fluorescence. And maybe that will help clarify why these are such different techniques and why they're so complementary and why fluorescence is such a pain in the Raman spectrum. Raman is a scattering technique, so meaning the laser light just bounces off the surface of your sample. It is a scatter. It is an instantaneous effect. Very few photons scatter through Raman scattering, so it's inherently a very weak process. And the laser light that bounces off is shifted in energy a tiny bit based on how it interacts with the molecular vibrations of your sample. So that tiny shift is what we call a Raman shift. And that is what we measure on the x-axis of a Raman spectrum. Whereas fluorescence is an absorption. And that involves a whole lot more photons and a whole lot more energy. And it is actually an absorption, a true absorption versus just like a bouncing, a scattering, and a later re-emission in time, meaning that process undergoes a longer lifetime. And that can actually be used to your advantage. And I'll show you why in a moment. So SuperCam and Sherlock both actually have a different strategy for mitigating fluorescence. Let me first start with SuperCam's mitigation strategy. The way SuperCam works is it is time resolved. Time resolution is basically when you take your Raman laser and your detector and you basically pulse the laser and you synchronize the detector, the CCD opening and closing in sync in such a way that instead of continuously bombarding that sample through the acquisition, you're pulsing the laser, and when the laser hits the sample and you get your Raman data, so you also get the fluorescence as well with it, which is in this diagram shown as this very broad gray many hundreds of wavelength in space effect. You can pulse the laser and basically gate out that longer lifetime fluorescence. So you can just capture that early part of the signal, which is what's being illustrated in that short gate there, and just chop it off, literally gate it out, and reduce that longer lifetime fluorescence. And so that's the way SuperCam can remove fluorescence. if you're dealing with a 532 nanometer excitation, which is generally the standard excitation for many lab and the two Mars rover instruments, the SuperCam and the one on European Space Agency's rover. Sherlock, however, has a different excitation wavelength. It is a UV excitation laser, and so that actually creates mitigation for fluorescence in a totally different way. Here you're energetically separating out that fluorescence. So if you imagine the Raman spectrum, the Raman effect in wavelength space, as I'm showing here with an intensity axis, again, you're seeing that Raman information as these discrete little bands riding on top of this huge wave of background fluorescence. And by being in 532 in conventional excitation wavelengths, I don't know if my cursor is visible, but it's right here in the very central part of the fluorescence signal, which is where the you can see is the most intense part of that signal, which fluorescence is most intense in the visible. So 532 is smack dab in the middle of that intense fluorescence range, which is why conventional Raman instruments often suffer fluorescence, particularly in Mars analog studies, where you're using aqueous lithologies that are relevant to preserving biosignatures. For example, you may have heard of, sulfates and phyllosilicates being good preservers of biosignatures. Those samples are probably the worst in terms of fluorescence. So if you go down in wavelength, meaning towards the UV, you can see how you're getting towards the tail of that fluorescence. So you're energetically separating out that huge fluorescence, and the Raman information does come out more clearly. So Sherlock is a 248.6 nanometer excitation laser. This is the deep UV. And I've worked with a team at the University of York University in Toronto, under the leadership of Mike Daly. So he's got a really great planetary analogs instrumentation lab, and he's got a UV system that's 266 nanometers. So right there, close, but it's not deep UV, it's just UV. And so some of the UV Raman and fluorescence work that I've done has been in collaboration with his students and postdocs, and I like to call their system the best kept secret in the Mars analog world, because aside from the actual Sherlock breadboard, there is not a better match for a UV system where we can do these informing type studies to understand how the Sherlock system works. And the Sherlock breadboard is so oversubscribed that it's often advantageous to go to a system like this that is not quite the official breadboard, but something very similar to it, where we can do our lab analyses. And so this is one of the reasons why Sherlock is UV. It's also because in the UV you're resonant to the type of biosignatures that are most likely to be found, aromatic organic molecules. So hopefully that is supposed to increase their sensitivity in the UV and make them detectable better. So I'm going to describe this study we did to really understand how well UV Raman spectroscopy reduces fluorescence using that 266 nanometer UV system. So for this study, we took a variety of basically Mars analog samples, natural samples, I should say. So these are samples made by nature, meaning they're messier and more complex than something we could have synthesized in the lab. And I'm always a big fan of using natural samples, because it helps you define the challenges a lot more clearly than using synthetic samples oftentimes. Of course, oftentimes you do need to use synthetic samples, but when possible, I like to use natural samples, and this is one case where that was helpful to see the challenges here. So I'm just showing the Raman spectra of these, the shale, evaporites, limestones, a variety of samples that are considered natural Mars analogs that are known to host kerogen, macromolecular organics, biogenically formed, which we know were biogenically formed in these samples. And so for this study, we looked at how well we could see the biosignature, and sure enough, you can see the signature of kerogen right around roughly 1600 in most of the samples, except in one. In this iron-rich mudstone here in the second spectrum, you're basically you're seeing basically a flat spectrum with just background. This is artifacts. This is not real compositional information. So we were not able to see anything. And you can see that the fluorescence does not really affect our analyses here, because you can see that it is energetically separated as we had hoped, and it only starts at this very, very end of the spectrum in a location where there's not a whole lot of compositional information relevant to us. So that's great news. So let me focus on this iron-rich mudstone here. This sample actually came from an evaporite playa in central Arizona, where I did my PhD with Jack Farmer. We had this great field site, which we defined to be an analog in our 2018 paper. We defined it as a Mars analog for the first time. And actually, I recently worked with NASA Goddard's Analog Explorer tool to highlight what a really cool, Mars analog this site is. And I encourage you to go. I'm just going to give a plug for this really cool site. I encourage you to go to this website and play with this yourself. You can basically see a variety of planetary analogs in a sort of side-by-side view using this tool, where you can see the terrestrial photo and then the planetary target kind of side by side, and you can slide this little curtain back and forth, and you can have a lot of fun playing with Mars and other analog field sites. Anyway, back to Verde Valley. So this sample is actually rich in iron phases. Of course, hematites and iron-rich alteration rims, and actually that was the reason for which we had a problem in the Raman spectrum. We concluded that it was actually strong UV absorption near this UV laser's excitation wavelength, so like near that 250, 260 nanometer region, caused by iron coordination complexes that basically just causes a whole lot of UV absorption, and you don't get a lot of Raman signal because of that. The good news in this work was that, yes, we were able to detect the kerogen as well as its hosting mineral matrix successfully in these challenging analog samples using the UV system. And before we really panic about how much iron is going to affect these studies on Mars, because Mars is a very iron-rich planet, needless to say, we really need to do more work to understand how and why and which types of phases and which concentrations of these phases would impact Sherlock measurements. And this is still ongoing work. So let me turn to the fluorescence, the lesser-known fluorescence analyses, the other side of the coin here, and show you how harnessing the power of the fluorescence side can really be an advantage for identifying potential biosignatures using a system like Sherlock. So here I'm showing in this leftmost panel basically the same spots that we targeted with the Raman and that we could see in microscopy analyses had these dark regions that we were pretty sure were kerogen. And this is what their fluorescence spectra look like. They have this broad feature that peaks roughly at like 425, 430 nanometers. It's a very imprecise, fluorescence spectroscopy is very imprecise as compared to Raman. But you can see morphologically the spectra are kind of similar. And I'm highlighting in this gray zone, I'm highlighting the range that Sherlock is tuned to see. So Sherlock was tuned and created to be an organic identification instrument. And for that reason, they had to have a trade-off in their wavelength space and shrink it down to a very small range. It's only about 250 to 360 nanometers, so only a little over 100 nanometers of fluorescence range that they can see. I'm comparing the spectra of these kerogen samples with basically other regions of the same samples where we were pretty sure there was not, at least not, visible regions of kerogen. So this is basically the mineral matrix everywhere else. And the good news here is that this double feature that you see in the second spectrum in all of these samples actually is also organic, and it has slightly different it has a slightly different spectrum than the Kerogen does, but similarly, it peaks in the 420 and the 440-ish nanometer region. And the other piece of really good news is that the same iron-rich mudstone from Verde Valley that I showed in the Raman spectrum does show a fluorescence spectrum of organics, where we were not able to detect anything on the Raman side because of the pesky UV absorption. We do see organic features. And so the first takeaway is that fluorescence from Kerogen does reveal a broad feature that is distinguishable from other organic features. And that organics were detected in the mudstone with fluorescence spectroscopy when they were not detected with the Raman spectroscopy side. So again, more good news. And you may wonder why we know that these are organic features in the second panel. It is actually because we took their lifetimes. You can take the decay of that fluorescence curve and get the lifetime of that fluorescence. And you can use that to say whether your sample has an organic origin or not. And so I don't want to get too much into this analysis. It's in the paper, but basically that's what I just said. This is a visualization of it. You can take imagine that spectrum I showed you and just sort of like time slice it through that long fluorescing, exponentially decaying fluorescence curve. And you can basically obtain the lifetime and lifetimes for organics and everything else, basically things that are like not organic in origin in a mineral matrix, like defects, like rare earth elements, like other types of impurities, have significantly different lifetimes on the order of three orders of magnitude different. So that's how we can identify organics, and that's how we did that. And that's how we were able to say that these other organics were consistent these other bands were consistent with an organic origin. And so back to this fluorescence data, we also obtained data on mineral standards to sort of match to the minerals hosting these kerogens in these samples. And so when we did the mineral analyses, we got some very surprising results. Here's a panel of all the different, basically the main lithologies in these samples and their mineral standard counterparts. And you can see, again, in gray here is Sherlock's range. And you can see here that we have some very nice, very strong features smack dab in the middle of the organic region in mineral standards. So this caused us to scratch our heads a little bit. And this really prompted the next study that I'm going to talk about. Why are we getting organic fluorescence in mineral standards? And these are clean samples. I don't think this is an issue of contamination here. So for this study, I really wanted to understand what could cause basically a false positive biosignature detection. What could cause a feature in Sherlock's fluorescence range that's not organic? And so I scoured the literature, and I learned that actually in the material sciences literature, we have a lot of information on one particular rare earth element that has a beautiful feature right there, and this is at 266 laser excitation wavelength, which is the same wavelength that this UV system was. And it is cerium 3+. So cerium fluoresces in a range that seen in Sherlock could be interpreted as organic. And this is actually kind of a problem because cerium substitutes for cations like calcium in pretty much most minerals that have calcium in them. How much of a problem could this be on Mars at Jezero at the landing site of Perseverance? Well, I'm showing here basically an orbital map, a map created by Orbital Analyses way back in 2012, way before we launched, of the major geological units in Jezero, and also below that I'm showing a table of luminescent minerals, so luminescent or fluorescent minerals under UV excitation. Jezero has a lot of sulfates. Sulfates are luminescent. Jezero has a lot of carbonates. Carbonates are luminescent under UV. Pyroxenes, biosilicates, all luminescent under UV. So with this, it's reasonable to say that cerium is going to be present at Jezero and detectable by Sherlock. So this, from this, I wanted to understand, okay, well, what kind of biosignatures could cerium actually mimic? So we synthesized cerium in the form of cerium phosphate, and that's the two bottom spectra that you see here. And we compared it against basically a variety of organics, that mostly amino acids, that could be considered potential biosignatures. And you can see here that the two main features in cerium phosphate, I should say, it can differ in other minerals, but cerium and phosphate has these 320 and 338 nanometer features. And funny enough, tryptophan has almost the same features. They're a little bit off, and again, I've been trying to emphasize how imprecise fluorescence spectroscopy really is. So that's close enough to be a pretty good match. The features in fluorescence are not as narrow and discrete as in Raman spectroscopy, so that's why this is considered pretty much a good match. And from this, we can observe that cerium can mimic a tryptophan detection using UV fluorescence spectroscopy. Well, that was a pure cerium phosphate mineral standard. What happens if we look at cerium in the abundances expected at the surface of Mars, so much lower concentrations? To answer that, we basically doped, we took Mars analog soil, so this is MGS1. It's basically a synthetic soil created to mimic the composition of rock nest in Gale Crater. And we took that soil simulant, and we doped it with a variety of concentrations of cerium from 50 to 8,000 ppm. And these concentrations were based on abundances of cerium in meteorites. So these are, reasonable ranges expected on Mars. And you can see that in all of these cases, we just had a difference in intensity, but really in all of these cases, cerium can mimic this detection of tryptophan at a variety of concentrations, even those low enough to be expected on Mars. Even at 50, you can see in this blow up here in the top right here, this inset, that you definitely see that feature even at the lowest concentration. The two features, I mean. That's the fluorescence side of the story. But remember, Sherlock can get Raman and fluorescence data on the same spot of the same sample. So what happens when we subjected those cerium-doped Mars analog soils to Raman spectroscopy, to UV Raman spectroscopy? Well, the answer is not a whole lot, because you can see that this is pretty flat data, pretty compositionless data. Well, these little steps that you see here, this is an artifact of the optical system in the UV instruments. This is not composition. And this little band here at 0 is the laser line. So essentially, this is 0 data present. And we think that the UV system did not identify cerium in these cases because of, once again, the same issue with strong absorption of the Raman light in the UV wavelength. So once again, this UV absorption is a problem again. And I think these samples exemplify a signal suggesting a potential biosignature in the UV, but when you look at them under the Raman, there's no additional evidence provided by it to give you an answer one way or the other. And that these results may lead to an erroneous conclusion that fluorescent spectra constitute a potential biosignature when they're from cerium. And of course, in a caching scenario, when we're making these sampling and decisional, when we're making these sampling decisions on Mars, trying to assess should we cache this sample and bring it back to Earth for biosignature analysis, this is going to present a challenge. And so I'm going to end with basically a summary that I think Raman can detect organics and their mineral context pretty successfully. And that's why it's been valuable for biosignature detection. That's why it's been sought after and finally has seen its first successes with Percy on Mars this year. And combined, Raman and fluorescence spectroscopy enhanced the confidence of a biosignature detection, as we saw with the Verde Valley sample. Even still, We're seeing cases of both false negative, as with the Kerogen and the Verde Valley sample, and with the false positives, like with the cerium, for biosignature detection occurring at this UV excitation wavelength. And we really, really need to do more work to understand how this is going to affect Sherlock. We really need more lab studies on this issue. And I hope that these considerations can improve potential biosignature searches with similar instruments to Sherlock, not only on Mars, but on future missions to diverse planetary targets. And with that, I will say thank you. Go Percy, yay. And I am happy to take questions.